So today's going to be crazy. I finally figured out why time seemed to be moving like at triple speed. Is because we meet Wednesday, Friday, we don't have any class next week, just a final exam. So what's going to happen is really quickly we'll do the shape part of the cosmology and our modern view of it. Really quickly talk about dark energy, because that's important and modern, and then wrap up the class. But then online I'll post the stuff that we would have gotten to, which is kind of, icing on the cake about the relationship in between particle physics and cosmology, and then a little bit more detail on exactly what's going on in this whole dark energy thing, which I'll just really quickly gloss over. So we'll do Shape of the Universe, Exercise 10, the in-class part, where you guys get to play with balloons and your own ballooniverses, and then presentations finish the class. Okay? Yeah. Yeah, it's next Thursday, so the... again, because of this funny schedule, it doesn't show up on the final schedule proper. But yeah, okay. So that it's a lot. Yeah, it will be, but I haven't written it yet because I was giving a final yesterday and today to 100 or so students, so a little bit behind. Okay. Yeah, over the weekend, and you'll have. There might be like a half-hour time limit on it, but you have books and notes and stuff like that. Maybe ask, and then I don't know what my schedule is going to be like because I have stuff at SU. But during the normal class period, I should be free. So if enough people want to, we could have final exam review on Wednesday instead of class. We don't have class. Yeah. It's unclear as to whether or not the room will be open because it's final exam day for other classes. Yeah. Other questions? Okay. We're here. We work all the way from, things like constellations and the apparent movement of the sun through the zodiac to the crazy stuff. And we're studying the universe in general. And this is kind of our starting point, Newtonian Cosmology, and this is interesting because there's even a book called Einstein's Greatest Mistake. So it's very, even to this day, if you want to have a sensational pop science book, it's like Einstein was wrong or Einstein was extra right or something like that. But he was informed by this view too. So this is basically the start of modern cosmology. This is probably what Hubble would have grown up thinking when he was in his first astronomy class. Is this kind of clockwork Newtonian universe, is that it may have never been started. It could be infinite in space and time, which is a little bit unsettling. But what everybody did agree on, at least in the halls of academia, was that there's just kind of like this mechanical kind of clockwork motion of all of the celestial bodies, and the rules of the clock are Newton's laws. Okay, so there's a couple of mathematical and observational problems. Is that obviously if it's infinite in space and time, you've got these things like Olber's paradox. And it's not really true that in an infinite universe, if you're tugging on all sides of a solar system, everything's in stasis. In fact, everything would collapse. And Einstein actually recognized that, which led him to postulate his greatest mistake, which was unmistakified in 2000. But we care about the largest scale structure of the universe now. So our light posts have got to be galaxies. So your understanding of galaxies is going to be, and the most powerful things within them is going to be crucial for cosmology. So this is kind of like the stuff that's lighting our way. And again, the modern story starts with Edwin Hubble, who actually started kind of tamely and painstakingly observed some individual variable stars at the outskirts of the Andromeda galaxy and used Henrietta Swan-Leavitt's light curve period relationship, luminosity period relationship, to determine that this thing was way outside of our own galaxy. And then further, it's got some tremendous size, hundreds of thousands of light years and, million light years distant from us. Modern number is 2.5 million. Hubble got it a little bit less. Always dust, always calibration. And then he went on to show that all spiral galaxies were about the same size. So using a variety of techniques like their overall brightness and distance and looking for variable stars, basically through the kitchen sink of the day at it, which is great because now you have these standard rulers in the cosmos. And if you see a bigger spiral galaxy of that particular type, then you know that it's actually closer. So it's, what we take for granted in this picture, you have to work really hard for in the cosmos because you don't really know, grow up interacting with spiral galaxies. You don't know their intrinsic properties. So that's really great. Things are really far away. And the encore, of course, is once you're stumped as an astronomer, your knee-jerk reaction is I should take a spectra. And the spectra tell you that the farther they are, the more redshifted, strong, in this case, hydrogen emission lines are. So small spiral galaxy, apparently small spiral galaxy because it's far away. They're the same actual size. More redshifted from the laboratory line. Closer spiral galaxy, less redshifted. And if you suck it up and you take this data painstakingly, which you guys will do on the second part of the 10th exercise, and plot them, you get a line. It's the best line ever. It even goes through the origin. Why does this line go through the origin? Well, should there be a data point here? And what is that data point? So this would be a galaxy at some distance with some redshift. So what's the galaxy that's not very far away from us and not moving with respect to us? It is us. Yeah, so this is us. So that's why the line goes through 0, 0. And again, realize it's almost worth it if you've been through a little bit of even algebra-based physics and you know about vectors. It's worth it to just make sure that you understand the relativity of this graph in the sense that if there were alien observers on this galaxy, they would also create Hubble's diagram and they would also get the same slope. So this does not indicate that something terrible happened on Milky Way and we're sitting at the location of the Big Bang. The Big Bang happened everywhere. Okay. So this kind of sneered at for a little bit, and then actually the debate went on for a very long time, surprisingly. And there's a kind of maxim in science that people don't prove their ideas and win people over to their side. They just wait for the old tenured professors to die. And then the correct idea takes hold. So as late as 1965, people were still dreaming up this solid state cosmos thing until two physicists pretending to be astronomers enough so that they took a spectrum noticed that the staticky hiss that was observable everywhere in the microwave bands was a Blackbody spectrum, and an incredibly perfect Blackbody spectrum from all parts of the sky, left, right, center, up, down, and it was all 2.71 degrees above absolute zero, which agrees with the theoretical prediction that people working on the Big Bang came out with that said, hey, if we had a Big Bang, obviously things are going to be, as more matter piles up on top of more matter and more matter, if you play the clock backwards, temperatures and densities are going to go through the roof. So if you start basically at infinity at the Big Bang and then you let it cool down for 10 billion years or so, you'll get this. Star-forming clouds are colder than liquid nitrogen, like 30 K. That's 30 above absolute zero. 2.7 is enough where you're almost at having superfluid, quantum effect, liquid helium and stuff like that. So it's very, very, very cold. But it's had 13.7 billion years to cool down. So we now believe it. And these guys got a Nobel Prize for potentially cleaning out pigeon shit. Okay, so that's the time thing. Any questions about that? Now this is where things get a little bit wacky, because maybe you have this image in your head, or you just totally wash your hands of it and say, we're at the center of what we can see, and it's beyond my, my place to question what's outside of that observational sphere. But you kind of have this idea of a box of galaxies, and is the box of galaxies expanding? What's at the edge of the box? This is, it can't be infinite, or else we'd have Olber's paradox in an infinitely old universe. Now we have a finitely old universe. Do we still have Olber's paradox if we're infinite? Are you unsettled by an infinitude of matter? The modern way of addressing this question is actually through general relativity, which we actually used locally when we were just talking about black holes and light. But it actually has some consequences for the entire universe. So GR says that if I have space and time, and they're not separate things, it's space-time. You can move really fast in space and then slow down time. It's all connected. If I put a big object, compact object like a sun, down in the middle of space-time, what it does is it kind of curves the space around it. So it's not right to think about these instantaneous forces of gravity where comets look at the sun and pull out their pocket calculator like you guys did on the middle exercises and calculate things. They're just moving through warped space-time themselves. And in the extreme case, you get something like a black hole where you're so warped that light couldn't even escape. So these, we've talked about this before, but we talked about little things. Pop a planet in there, or a sun, or a little thing like a black hole. Now that we're talking about cosmology, you actually have to consider this too, and this is the right way of talking about the shape of the universe, is that the overall amount of matter, add up the dark matter, add up the luminous matter, add up all the radiation, everything that has energy and therefore warps space-time, you're actually, as well as all the dimples, you're going to get this overall curvature of space and time. And what this could do, and this is, it's made people really happy for a while, I think, is that, let's talk about closed first, is that, imagine these dimples like in the muffin pan or whatever in the golf ball is, I'm just plopping a galaxy or a cluster of galaxies, little bits of mass there. As well as their individual, dimpling effect, there's the overall effect where they curve all of space-time globally. And what you could get is that if you had so much matter and so much energy, you could actually close space-time. You could have it so curved that it closes back on itself, which is nice because it takes a finite amount of stuff to make a closed surface. So there are no edges here. There's just so much mass and energy that we've actually curved all the way around. And phew, we don't have an edge of the universe that I have to worry about being pushed off of. And what you thought before is what people call, probably, is a flat space-time, where everything's completely flat. There's actually just the right amount of matter and energy where it curves just enough to make it flat. There's a third possibility called an open universe. But this is the absolute prediction of GR is that you add more and more and more matter to the universe and you'll get it to have an overall curvature, which could be closed. Saves you from this problem. You don't have to have an infinite amount of stuff. And that's kind of what people thought they would have. So what do those shapes exactly look like? Well, you kind of make an assumption, and so far nobody's been able to disprove it. I mean, the uniformity of the cosmic microwave background radiation is a really good indication too, is that the slide is, it's definitely, artistic representation from the Pearson Education Incorporated company, but that's kind of what the universe looks like. So when I show you a picture of, for instance, a Hubble field, you can't say like, oh, that's the really dense part of the universe. It all looks very, very even. So what that means is the overall curvature of the universe should be very even too. So it should always be the same curvature no matter where you are. So the universe can't be like, the 3D equivalent of a potato shape or something like that. Okay. Which means you have exactly 3 options. And these are the 2D cartoons of them, and we'll talk about how you would observe this in 3D. So it's really hard to, draw 3D closed surfaces because we live in what's effectively a flat 3D surface. And you'll realize what that means in a couple of minutes. So what closed means is, it's caused by we would have more than some critical amount of mass. Everything bends inwards. So what this means, for instance, if you're a little two-dimensional person, let's say we're ants and we live on the surface of this thing, I could walk and walk and walk and I could end up back where I started. The universe has no edges. And there are some other consequences too. Or you could be in a flat universe. Flat geometry is what we're used to thinking about, where lines that start parallel remain parallel. You can make a triangle and the angles add up to 180 degrees. That would require, actually that's kind of weird because that requires the absolute perfect amount of mass and energy in the universe. So this is like balancing a pencil on its point. And then the third option is you could have an open universe, so says GR. And that would be if you just don't have enough matter and energy in the universe to pull itself back together. And what you would have is things would have a tendency to fly apart. So if you started, you and your friends started walking and you were parallel, eventually you would start going to the side. So a 2D open shape would be like a Pringles potato chip or a lily petal or something like that. Is, 2 beads of water on a lily petal will actually bend apart because of the way it's curved. So these are just snapshots at one particular time. It turns out that the expansion is absolutely related to the geometry, not the fact that it's expanding. You can have an expanding closed, open, or flat universe, but the way that the expansion changes is actually related to what type of universe you live in. And it's because there's no such thing as space and time, and the two problems are related. If you're closed in space, in particular, you got to be closed in time. So you have enough matter and energy to close yourself in space. You actually have enough matter and energy to have a big crunch at the end of your Big Bang. We'll get to that in a second. Yeah, absolutely, though. Okay, so these are 2D cartoons, and those are the names. How would you determine this in 3D? because we're not ants living on the surface of balloons. If you were in a 3D closed universe, what that would mean is take two of your friends, get very, very, faithfully navigating rockets. You go off in this direction, your friend goes off 90 degrees from you, and then you go off 90 degrees from them. So basically x-axis, y-axis, z-axis. In a closed universe, if you were very, very patient, what would you guys do? Yeah, eventually you would run into each other. So it seemed like you're just going in a straight line, and eventually you get back to where you started. Just as in 2D, if you were living on the surface of this, this two-dimensional surface, you walk around, you end up back where you started. That's obviously a really difficult experiment to perform, so we need to come up with some other consequences, which are a little bit, more technical and geeky. And they really have to do with Euclidean geometry. So in a closed universe, if you were to make a really big triangle, the angles would add up to more than 180 degrees. The triangle would kind of like bulge out a little bit. You can try to visualize that, but I'll show you guys a picture later. And then secondly, if you had two initially parallel lines, you can do this on the surface of Earth, is that you and your friend are at the equator and you just walk north along your lines of latitude, and eventually you guys will meet at the North Pole. Longitude. And that would happen here. So you and your friend, instead of traveling in a full circle and, really experiencing the closure of the universe, you have two laser pointers and you start them parallel. By the time they get 10 billion light years away, they will have intersected, no matter how carefully you made them parallel. Yeah. So that's closed. And people kind of want that because it actually does mean that, or want it, that you have no edge problem. You don't have this infinity thing. The universe does have a finite amount of matter in it. It's just of some, appreciably big enough density. Okay. Flat universe, just 3D version of this. It's like a box, make a triangle, the angles add up to 180 degrees, parallel lines remain parallel. You keep walking in some direction, you're never coming back. There's an infinitude of places to go. And open universe is basically all of the consequences from the closed universe are flipped. This is also infinite. There's no, you and your friends walk initially parallel in an open universe, or you shine laser pointers. Eventually they'll diverge. So there's just not enough matter and energy to hold things together. And if you were to draw a big triangle, the angles of the triangle would be less than 180 degrees. You see them kind of bow in a little bit. So to test this, you either need to trust the math and you need to count up all the matter and energy. We've been burned by that before. But it would also be nice to actually do something like this. Find a giant triangle in space, right? And see if we can measure the angles of it. But any questions about that? Okay, so this is actually, I will say this is not new. You've learned this stuff so far in the past that, if you did have a kindergarten teacher who said, this is really interesting, this fifth postulate about parallel lines is that people realized, even when they were doing these proofs with compasses and rulers and all this hokey stuff, is that you didn't necessarily have to have this. So the geometry of the universe doesn't have to be the geometry of a flat piece of paper. It's just really convenient for humans. And as far back as Euclid, again, these guys, 3rd century BC was a wonderful time, I guess, is that people were talking about this and what if this, this initially parallel lines, what if they did meet, or what if they did, get farther away? So it wasn't actually required. It isn't required. And this is obviously well before general relativity. And there's a resurgence of thought in this. Actually, all the math, the terrible, terrible math of GR comes from this 19th century kind of resurgence in interest in open and closed geometries. And famous mathematician C.F. Gauss, he actually got off his backside and organized the survey of Germany wasn't a country, it was a bunch of German states. He organized the survey of Hanover, and he had people and himself get on the tops of mountains and kind of do the math of just figuring out how far away things were, how high mountains were. Very boring work for a elite mathematician. But why did he care about this? He was subtly gathering data, and he wanted to know if, for instance, the sides of these the angles of these triangles added up to 180 or not. So actually, we don't have to live in a closed universe, a flat universe. We could live in a closed or open one. He measured nothing, so it turns out that you would have to have a much bigger triangle, and you know how big the triangle is in a second, or will know. to measure this. But this is actually a kind of old idea, is that the universe does not have to be infinite and flat. Like the intrinsic geometry of where we live could just, be different. It doesn't have to be flat. Okay, so these are some of the pictures. So I try to draw a triangle on a closed geometry. I could even make them 90, 90, 90, so 270 degrees. Triangle and flat geometry, just normal triangle things. All these lines start parallel, remain parallel. These two lines actually started parallel. They're separated by 90 degrees. They converge. And in an open universe, see this skinny, skinny angles on these triangles, less than 180 degrees. And even if I do an amazing job of starting lines parallel, they'll diverge. It's that, but it's in 3D. So you'd actually have to do the experiment with lasers or something like that. Fortunately, there's light flying all around the universe. Okay. Yeah, parallel lines, well, in the closed universe, parallel lines would converge. And in an open universe, parallel lines would diverge, initially parallel lines. Yeah. Okay, so why don't you notice this on a day-to-day basis? In fact, we can't even figure out, it's this not true, but they tell you in kindergarten that Christopher Columbus proved the world was round. Why was that in any sort of debate? This is Kansas. If you were a primitive human living in the plains of Kansas, was it obvious to you that the universe or the world was round? No. So there's this phenomenon that we actually call, wonderfully descriptive name is local flatness. And it's the fact that if the curvature is so small, open, closed, whatever, it's just a very, very small amount of curvature. It's just hard to tell. Because right there in your backyard, it looks very flat. The joke is, I was in Nebraska and my dog ran away. I watched him for 4 days. Okay. So local flatness takes on just absurd proportions in the cosmos. So we've sent things outside of our solar system. We've never experienced any sort of weirdness. The Pioneer probes are still going, in the geometry that we would expect based on local flatness. We can look at light traveling in between galaxies. Everything seems to be locally flat. What we really need, because we didn't observe this or worry about it until now, is we would need a triangle that's on this sort of size, right? So these are all galaxies. So we've made triangles on the surface of Earth. We haven't measured this. There's LIGO in Hanford that's basically like a big triangle. It detects little ripples, but not the big curvature. LISA, which might go up in space, actually is a big triangle in space, but separated by 500,000 kilometers or so. So you're not going to see this. So should we give up? Are we ever going to construct an experiment that makes a triangle separated by billions of light years? There's a trick, and this is really, really fortunate. So nobody, Hubble, nobody else could really see any deviations from local flatness. The answer came in about 2001, which is why this is a little bit new and integrated awkwardly into textbooks even now. But the answer comes from two things. One is look-back time, and two is the idea of space and time not being separated. They're actually the same thing. So, again, warpages in space, warpages in time, and you actually don't have an option. If you're closed in space, you're closed in time. If you're critical or flat in space, you're critical or flat in time. And if you're open in space, you're open in time. So these would be what you would call the Big Crunch scenario, closed in time, is that, things expand away from the Big Bang. There's so much matter and energy that things are going to be pulled back together into a big crunch. So start and end at a single point. And this would be associated with closed geometry. It's got to be. So that's hardwired into relativity. You could have the flat or critical, which is kind of interesting. It would be like rolling a ball up a hill and having it stop right at the top. So it slows down and slows down almost infinitely so. And this, again, takes this weird, perfect, knife edge amount of energy. So it's actually remarkable that we see a flat-ish universe. And then finally, this thing called the Big Chill, which is an accelerated universe. So it's open. Everything flies apart. All the stars burn out. There's no new sources of matter. Nothing interacts. Eventually the M stars go, and there's just this flat, dead, boring universe. So that would be an open universe. Just not enough mass and energy to pull everything back together. So building a triangle with 2 billion light-year sides would be hard. However, this, which is the equivalent question, look back in time is equivalent to looking far in space. We can do this. We can absolutely do this, because if you look at something that's 10 billion light years away, which we now have the technology to do, what are you doing? Looking at something 10 billion years back in time. So you're actually getting this slice of what the universe looked like. Okay. Any questions about that? Things just got really weird in the last 15 minutes. No. So the problem is we're not there yet, and this is what we'll pick up after the exercise, is that the so-called distance ladder, which is how we find distances to things, because you do need to calibrate them. If you don't know the distance, you don't know the time. If you don't have really good measurements of the time, you're not really getting a good sense of whether or not the universe is speeding up or slowing down or cruising to a halt. And the only one we have so far is redshift, aka Hubble's law. And you can't use something to test itself. So the only reason we know about the expansion of the universe is through Hubble's law. We can't use Hubble's law to test the expansion of the universe. So it's kind of circular. So we need something else. And that something else will be weird little tiny stars. But we'll get to that after exercise 10. So any questions about that stuff? Yeah. Yep. No, so this kind of foamy latte stuff that you see out to about 10 billion light years, we don't know if that it's the biggest distance scale, and every once in a while somebody comes up with an idea that we're actually in what's called a super Hubble mode expansion. So outside of our bubble that we're at the center of, there's less density. And imagine that you took an above-ground pool and all at once you just ripped off the sides, so all the water would flow out and everything would seem to be expanding from the center. So that would be kind of what the universe is doing. So kind of a philosophical red flag that raises. It puts us where? At the center, at a privileged point. And so there's this principle that you shouldn't do that. And if you come up with a theory or idea that says that you're at the center of this special place, then it's probably not true. We've been burned by that so many times. The Earth is not at the center of the solar system. The solar system is not at the center of the galaxy. Now somebody's going to revive this new Copernican theory that the galaxy is at the center of the super Hubble mode expansion, which is faking our accelerated universe. But yeah, people do talk about that, and there's no guarantee whatsoever. So. Yeah, actually, very well-renowned people, at the University of Chicago, came out with this because they were so offended by the accelerating universe data, I guess. Yeah. Other questions? Yep. Yeah, so what's the universe expanding into? This is a terrible quirk of the English language. So when you pour cupcake batter into cupcake trays and then bake them, the cupcakes expand, and they expand into the rest of the oven. The real way that you should say it just doesn't have the same ring, is that the average distances in between particles is increasing. There's no extra universe stuff that the universe is taking up more and more of. So the universe is everything that there ever is and ever will be, so it's everything, but it's just the average distances in between everything are increasing. And there's nothing outside of that we're kind of, we're encroaching upon. But it's kind of like a quirk of language that we say expand into, and you always think about, this kind of capitalistic zero-sum thing where I'm taking stuff or space from somebody else, or leaking across the back of the car seat onto my sister's side or something like that. But it's not true. It's just the average distances in between things are increasing. Yeah. Other questions? Okay. So I need to